Hello, students. Sorry you can't see my face, but the video editor is not appreciating the camera today, so I just have to do it with audio. So hopefully we can get this recording done. We are going to be learning about logic and reasoning. These are both elements that you have been using in your critical analysis, but you don't necessarily know the names of all the things that you've been using so far. Again, if I was the one designing all the Edgenuity lessons, I would be putting logic and reasoning before your critical analysis. But c'est la vie. Here we go. Logic. Logic is reasoning or thought guided by a set of rules. Up till now, you haven't really been following a particular set of rules when you are using logic. One example of logic in popular culture is, of course, Mr. Spock or any other Vulcans from Star Trek. They follow logical tenets and believe in logic as a way to perceive the universe. So we are all Vulcans today, and we are going to use some logic to break down some examples. The types of logic we'll discuss are mathematical logic, deductive reasoning, and its opposite, inductive reasoning, and then abductive reasoning. And finally, we'll take a look at some informal or incorrect logic. Mathematical. You know mathematical logic through the form of, numerology. 1 plus 1 equals 2. Therefore, 2 minus 1 equals, 1, right? You'll do a lot more of this in algebra, which looks kind of like this. It takes that equal sign and puts it on the other side. So here, 1 plus 1 is equal to 2, right? Or if they say 2 minus 1 is equal to what, you are finding out that what by taking 2 and subtracting 1 from it. But mathematical logic can also be applied in the opposite direction. An equal sign just means that both things on either side are equal. That's why it's called an equation. Here, I've taken the equal sign and put it on the opposite side. You see that it just says 2, right? 2 is equal to or balanced with x minus 28. Whatever x is, if you subtract 28 from it, you will get 2. So just do a little bit of math. Yeah, there you go. 30, right? 30 minus 28 is 2. Some more mathematical reasoning. This is called the transitive property. You might have heard of it, you might not. It says if A is equal to B and B is equal to C, then A must be equal to C as well. Because A and B are equal, A and C must also be equal because B is equal to C, right? So it all follows through. Okay, let's get off of math because we're talking about logic, and you can ask your math teacher about that if you want. Okay, deductive reasoning. This is probably the most famous form of logic because it has kind of fallen into popular culture along with Sherlock Holmes, which is funny because Sherlock Holmes doesn't really actually use much deductive reasoning. So we will talk about the type of logic that he does use, but that is not it. Okay, deductive reasoning, people like to use, let's think about this deductively, or let's use some deductive reasoning to come up with this answer. They're oftentimes not actually using deductive reasoning. Basically, deductive reasoning looks like this. You take general principles and then you return to specific instances. So you take some larger ideas, make some rules, and then deduce what the specific instances or examples are. So here is an example. These are rules. All triangles only have 3 sides. A yield sign has only 3 sides. Therefore, a yield sign must be a triangle. This is deductive reasoning, and it follows. We made some rules. All triangles only have 3 sides, and a yield sign only has 3 sides. Therefore, a yield sign must be a triangle. It works. It follows. The biggest rule for deductive reasoning is that your last result, your conclusion, your therefore, it must be true. If your conclusion might not be true, it is not deductive reasoning, or at least that deductive reasoning is not complete. So let's look at some faulty logic. All triangles have 3 sides. A stop sign has 3 sides. Therefore, a stop sign must be a triangle. Okay, so what's the problem here? Obviously, a stop sign isn't a triangle, but on the surface of it, all of these things look true. All triangles have three sides. That is true. A stop sign has three sides. That is also true. Therefore, a stop sign must be a triangle. Well, there must be a problem here, right? If you notice, there's one word that's different. A yield sign only has three sides. See that? Here, a stop sign has three sides. What it should say is a stop sign only has three sides. If that were to be tested, we would realize that that is not true. And therefore, our conclusion cannot be true. All triangles have three sides. That is true, but we should probably say all triangles only have three sides in order to prevent any other similar issues from occurring. Now, let's look at inductive reasoning. Inductive reasoning is the opposite of deductive reasoning. Rather than going from general rules, like all triangles have three sides, we use specific instances to build up to a rule. Inductive reasoning is one of the most common forms of logic used, and it's actually a little bit dangerous when it's used improperly. Inductive reasoning is problematic at times because it's what allows us to build up stereotypes. There's nothing wrong with inductive reasoning, but it's oftentimes used to use specific instances as an excuse to form general principles. Let me give you an example. If we were using deductive reasoning, there is no way that one could take a general principle about a cat and apply it to specific instances of a cat that would be unfair. You could say that all cats have retractable claws, and that would be true because that's one of the things about cats is that their claws retract into their feet. Therefore, any specific instance of a cat would have retractable claws. However, if you were looking at specific animals of a particular species, and then you had to go backwards to general principles, you might end up with some problems. Say, for instance, the first mammal that you ever saw was a platypus. You might assume, based on the specific instance of a platypus, that all mammals lay eggs, or all mammals have a bill. But that's not accurate, at least not for the general principle of mammals. You might say, based on a whale, that all mammals live in the ocean. Again, that is not true. So using specific instances to build up to general principles requires a lot of those specific instances. You need hundreds or thousands of pieces of evidence to really build a rule based on inductive reasoning. However, we can do it, and that is actually the core of science, is by gathering data, you can form a hypothesis, look for expected results and observations, check your actual results and observations, and eventually form a core theory. And that core theory becomes a general principle from which you can then do more things. So, for instance, the theory of gravity. We theorize that when mass is applied to the space-time continuum, that fabric of space, the mass attracts other massive objects. That, two objects will attract one another. And this general rule can then be used to make more rules, like when two objects collide, they will produce an equal and opposite force, and so on and so forth. So inductive reasoning is extremely helpful for things like science and gathering data. However, again, let's go back to this specific instance to general principles. Inductive reasoning can be a problem when you use a few specific instances to create a general principle, such as all children are lazy. That's not an accurate general principle, but if you have a son who isn't doing a lot of work, or you meet a lot of classmates or a lot of students who aren't doing a lot of work, and it seems like all of your kids aren't doing their work, they're all so lazy, you might form the general principle that all young people are lazy, when really it's just that you've met a few specific individuals who are lazy. And this follows for any stereotype. You could say, all Chinese food places are run by a family. Well, yeah, a lot of them are, but that's not a rule. You can't say that all Chinese food places are run by a single family. Look at Panda Express. That it clearly breaks that rule. Therefore, that rule is not true. Moving on. From inductive reasoning, we're going to go to abductive reasoning. Now, this is my personal favorite, not because it is any more true or accurate than any other form of logical reasoning, but because it's the one that most applies to literature. When you are reading a story, you don't always have all the information. And as a result, you sometimes have to draw your own conclusions. And that's really what abductive reasoning is about. You're thinking abstractly to draw conclusions. If we go back to this slide, we can see that specific instances lead to inductive reasoning, which can create general principles, or general principles can go down to deductive reasoning, which allows us to identify specific instances. But abductive reasoning actually breaks this cycle altogether. You can use specific instances to then infer what happened in a different specific instance. So we skip creating general principles at all. There are no rules being made. There's simply observations and theories being created and destroyed all at once. So for instance, two men are walking down the road and they see a dark figure under a streetlight. Man A, decides to stop and take a different path. He arrives home safely. The other man, Man B, does not arrive home that night. Why did Man B not arrive home? Now, when you look at this, it's very tempting to say that the dark figure caused the man to not arrive home that night. Why? Because that's all the information we have. And as a result, it's very tempting to draw a conclusion that somehow this dark figure was involved with Man B disappearing. The problem is we don't really know that not arriving home is a problem, right? Why did Man B not arrive home? Who knows? He might be going to work. Maybe he works the night shift and he didn't arrive home that night because he never arrives home that night. Maybe he got lost and the dark figure was nothing. Maybe it was just a mailbox. We don't know. So drawing conclusions based on limited information like this leads us to all these crazy theories. So generally, when we do abductive reasoning, we're using abductive reasoning to create an inference that makes the most sense. This is so vague that we can't really make a good abductive thought. We can't really draw a conclusion here. But let's try one like this. You are searching for a missing friend. You go to their house and find that there is a bowl of their favorite soup on the counter. It is still hot. What can you assume based on this? Now we have something that we can actually do a little bit of abductive reasoning on. So you think your friend is missing, but when you go to their house, you find that there's a bowl of their favorite soup and it's still hot. If the soup is still hot, then what recently has to have happened? Obviously, somebody must have heated it up. If it's their favorite soup, one might assume that it's either made by them or somebody very close to them. And they're probably around. They might be in the house somewhere, or they might have just left and are coming back shortly. Otherwise, why would they have heated up the soup? So it's this kind of abductive reasoning that's very useful to us. We can use little bits of information to draw deeper conclusions. Now let's take a look at faulty logic. Logic that is being applied in a very, very poor way. Here we have what's called informal logic. Informal logic is basically a term for deductive reasoning that's done wrong. So here you may recognize how this statement is formed. Only people who get tested for COVID-19 are diagnosed with it. People who get tested are more likely to wear masks. Therefore, wearing a mask makes you more likely to get COVID-19. Okay, so there's a few problems here, but the point is that this is the type of logic that you may see applied to certain situations. You may hear people forming these sort of logical sounding arguments, but they don't actually hold up to any kind of scrutiny. Remember what I said about deductive reasoning and the tests we do for it? Every general rule, meaning these two statements, must be true before this rule can be true based on the previous two statements. The conclusion has to be the only possible conclusion that one could draw from those two prior statements. So let's just start with the first one. Are these two statements true? Only people who get get tested for COVID-19 are diagnosed with it. This is actually kind of true. You can't really know if you had COVID-19, therefore you can't be diagnosed with it unless you get tested. Now, a doctor could, in theory, look for signs and symptoms and say, yeah, based on your proximity and your signs and symptoms, you got it. But that could be perceived as a kind of test. So yeah, we could actually say that this first one, under scrutiny, does follow suit with a good general rule. This is a fine general rule. Only people who get tested for COVID-19 are diagnosed with it. Sure, because you cannot make a diagnosis without some kind of test. People who get tested are more likely to wear masks. Okay, well, now we have a little bit of a problem. More likely? What does that mean? More likely is a statement that should never appear in any kind of deductive reasoning. You would have to say something like, only people who get tested wear masks. Now, and then we're not really doing deductive reasoning. We're forming logical conclusions based on evidence. That's what again? That's inductive reasoning. Inductive reasoning is taking observations and then drawing general conclusions. So this is actually doing the opposite, right in the middle of a supposedly deductive argument. Therefore, wearing a mask makes you more likely to get COVID-19. This is obviously false because the second observation is false. And there you have it, a logical sounding argument being taken apart by its own logical rules.